Most businesses I've talked to recently want to build agents to solve their problems and automate the processes. There's a lot of hype around agents, um, uh, the miraculous thing that they can do. Also, there are tons of frameworks that you have to choose from and abstractions that you have to navigate to decide how to build your agents, and it's very hard to choose among them. In this video, I'm going to review this excellent article, Building Effective Agents by researchers at Anthropic. Uh, After seeing so much hype around agents, it is really refreshing to see a keep it simple article, which goes right to the heart of building agents, avoiding unnecessary abstractions, and keeping it very simple all throughout, avoiding complexity. So in this post we share what we have learned from working with our customers and building agents ourselves. So there's a lot of practical advice, and you can trust because they have been building themselves, and they are a very popular language model provider. So first, the tricky question: what are agents? The agents definition of agents is really, it's a big hurdle. Everybody defines agents in their own way, and so they choose to define agents as fully autonomous systems that operate independently over extended periods using various tools to accomplish complex tasks. So autonomous, independent, extended periods, and tools. So they all call these systems agentic systems and make a distinction between workflows and agents. So that's the only distinction that they make between workflows and agents. The workflows are systems where LLMs tools are orchestrated through predefined code paths. Agents, on the other hand, are systems where LLMs dynamically decide their own processes and tool usage. So essential idea is that when the control flow is predetermined and human has enough information to decide how the different tasks are orchestrated. Now, any one or more tasks could definitely involve calling LLMs, but the overall orchestration control flow is predefined by a human and is can be directly implemented. So those flows are called workflows. Agents, on the other hand, are places where things are dynamic, where you don't know how many subtasks you're going to or which of those you're going to route to, how is your task going to be decomposed. So when the control flow is pretty non-deterministic, and it's very hard for a human to define it precisely at the start. That's where full-blown autonomous agents come in. So so the article first talks about these workflows, several kinds of workflows, which are relatively deterministic patterns, architectural patterns, and then finally about agents where the language models have more control in deciding which paths to execute, or have full control in deciding. Again, before we go into the frameworks and the architectural patterns, the good thing about this article is that it really keeps it simple. It advocates to really keep agent design simple. This might not mean building agentic systems at all. Okay, we recommend finding simplest solution possible and only increasing complexity when needed. This is the take-home message of this article. Avoid building or thinking about agents when you can build it more deterministic systems. Your system is more deterministic, and even though it depends on LLMs, the overall architecture is deterministic. When more complexity is warranted, workflows offer predictability and consistency for well-defined tasks. Agents are better option when flexibility and model-driven decision making are needed at scale. And for many applications, optimizing a single LLM calls with retrieval and in context is usually enough. So essentially, a basic RAG setup with tools is good enough for many applications, and it's a waste of time and to 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 model these systems as complex agents and introduce several abstractions which only add technical depth and make it harder to modify the system later on. That's the take home message of this article, and it's really important to keep in mind because this is the most common mistake almost everybody I talk to makes. They try to use these complex frameworks which have opaque abstractions and make their life harder, whereas the solving the problem that they really wanted to doesn't need all that complexity, right? Yeah. Again, the other refreshing thing about this is that it doesn't really advise you to jump into a framework or adopt a framework completely to solve your task. Instead, it advises, the article says that you should be more cautious in picking a framework. So these frameworks make it easy to get started they provide layer over LLMs, calling LLMs, parsing tools, chaining calls. But the issue is that they often add extra layers of abstraction that can obscure the underlying prompts. Knowing the prompts is extremely important, and not just knowing them, tweaking them, extremely important for getting that task, getting your program working correctly, and not being able to see the prompts easily. The prompts are often hidden behind layers of abstractions. That makes it really hard to figure out what's going on and to debug when you face an error, right? So the hype and plus the way so many examples with each of the frameworks make it tempting to add complexity when a simpler setup would suffice, right? So the overall advice is that if you do use a framework, ensure that you understand the underlying code. And this goes both ways. You can always start from scratch, get inspired by these frameworks, and build a minimal framework for your use. Or if you think that a framework offers a host of functionality that you won't want to rewrite, you should first go and understand the code deeply, and then go ahead and. Great. So now let's look at the building blocks for these agents. They've defined very nice architectural diagrams that distinguish between different architectural setups that you may use to use LLMs together with agents and to solve your problems. So we're going to deconstruct these architecture diagrams, and throughout I'm going to draw an analogy between the diagram and basic programming primitives, right? So you'll see that these architectures are not really new. But how LLMs are used, how LLMs are used in the different setups can vary. Right, so the basic setup, the augmented LLM, is essentially you have a query, input query, it goes to an LLM, and the LLM has a bunch of tools. It can access them, and it can query, for example, retrieval engine, call tools like web search, and to maintain the context, the previous conversation, it has memory, and through repeated interactions with these, it's able to answer the query and give the output. So retrieval tools and memory, so this is the basic augmented LLM augmented with tools and memory. Right, so they say that we recommend two key aspects of the implementation: tailoring these capabilities to your specific use case and ensuring they provide an easily well-documented interface to it. For example, you can access many different data sources using something called Model Context Protocol that Anthropic released recently. And this provides a uniform protocol to access many different data sources, many different tools, from file systems to information in Google Drives. And right, so that's the first one. And now let's try to see what a more complicated, more complex architectural setup looks like. So this is chaining, prompt chaining, something that many of us are already familiar with. You get the input, you make an LLM call that gives an output. Depending on the output, this is essentially an if-then-else programming construct. If-then-else, if the values satisfy some conditions, then you call another program, a branch of the program, or you exit. Now the branch has a chain, it's a sequential composition of two LLM calls. The output of first goes into the output of second, and finally you get the output. Right, so prompt chaining and if-then-else. That is what this diagram stands for. Both are very common, well-known primitives. But how do you use LLMs? How do you place them in that control flow structure is key and unique to this implementation. Right, so they also say when to use this workflow. And for example, when you're using a marketing copy, translating different languages, or you're writing an outline, checking the outline, this is the gate, if, and then writing document based on the outline. Okay, so third workflow is routing. Routing is again a very pervasive construct. The diagram is pretty evident. You get the input, you call a router, again a gate, an if-then-else, but this time the router could be decided. The condition could be decided by an LLM itself, and depending on the output of the router, you switch into one of the branches, which can in turn make an LLM call. So what this ensures is separation of concerns between the three different tasks, and the router could itself call an LLM and be more sophisticated than a simple symbolic formula. When you use this workflow, there are distinct categories that are better handled separately, and you use the initial classifier router to decide where to go. Examples where routing is useful: different kinds of customer service queries, questions, refund, technical support, and there might be different modules or downstream processes that handles each kind of customer request, and so you route onto that module. Right, so next is parallelization. It's sort of a for loop with parallelization. The key is that you don't know how many subtasks you're going to create. So as you get a request, it needs to be solved by decomposition, solving multiple subtasks, but you don't know how many subtasks there are. So you make a parallel divide and parallel call LLM, and when you get the outputs of the LLM, you use an aggregator to combine the outputs in a way that makes sense. Right, so this is the typical for loop parallelized. Right. So, for example, use voting, where different prompts review and flag a piece of document or code, and the final result is a voting is a combination of the different results, so that you can have more confidence in the result. Right. On top of that, it is similar to the parallelization, except that there's a more heavyweight orchestrator, which breaks down the task and delegates to worker LLM synthesizes the results. So this is just one step above the simple for parallelized for loops. Both the orchestrator and the synthesizers could be more sophisticated here. Right. And the last, let's say, more deterministic workflow is that of a generator and an evaluator in a loop. So this is a while loop, and with two components, the generator and the evaluator. The evaluator looks at what generator presents and critiques it, either accepts it or rejects it in feedback, and so the generator can output a better result next time, better solution. Alright, so this is useful when there is a clear evaluation criteria and when iterative refinement provides measurable value. So there's some progress every time. It makes sense for us to have a separate evaluator, and getting the critique from it makes generator perform better. That is when you use this generate critique loop. This is a very nice analogy. It's analogous to iterative writing process. Human writer may go through and producing polished document. They write the initial version, they critique it, have feedback, and then they try to improve it. Okay, yeah. So next we move to agents which are dynamic flows, where LLMs have more say in what the control flow is going to be. What everybody is really excited about are these dynamic agents. These agents are begin their work with either command from or interaction discussion with the human user. And once the task is clear, agents plan and operate independently, potentially returning to human for further information or judgment. Now, this level of autonomy is very interesting for scaling up tasks that humans can conceive, and that's why this allows us to execute tasks in a coordinated fashion at a scale that is unimaginable. Now, agents can handle sophisticated tasks, but the implementation is often straightforward. That's a big conjecture. That's a big viewpoint that this article proposes. They're typically just LLMs using tools based on environmental feedback in a loop. So this is the diagram. This is a very simple diagram of an architecture of how an agent works. Human makes an LLM call. LLM call decides to make an action towards the environment. When the action finishes, you get some feedback from the environment, and the LLM decides whether the task is done or reformulates a task and repeats the process. Agents can be used for open-ended problems where it's difficult or impossible to predict the required number of steps, where you can't hard code a fixed path. So this allows autonomy and generality at an extreme level. So the simplicity of this diagram says that you can build agents to solve problems that are fairly undetermined. The control flow is fairly undetermined in the beginning, and through the actions and through the feedback from the environment, the agent figures out what are the next steps to do, and iteratively proceeds to solve the task. So in cases where it's very hard to come up with a fixed or predetermined workflow, or in cases where the task itself is not clear, you can use these autonomous agents to execute the task. See some quick examples where agents are useful. Coding agent to resolve the SWE bench tasks, which involve edits to many files based on task description. So given a task, the agent has to determine which files will be edited and how they will be edited. It's very hard to predetermine or define a control flow for such tasks. So all we can do is to guard these agents, is to sort of supervise these agents at a high level so that they execute the task properly. Other is computer use, where the cloud uses computer accomplishment. These are again very complex tasks, and while each actions might be clear, while clicking on a button or browsing a page or navigating to the next page, these actions, atomic actions, are known. The whole flow of how these actions are executed in sequence is not really clear in the beginning, and that's what the agents. So you set up the agents in a way that it can determine which of these, how to execute these actions in sequence, and get the whole task done. This nice messaging diagram shows how this SWE bench task is executed, starting with the initial query, clarify the query, and the interface sends the context to the LLM of the task, and LLM searches the files and writes code until the task is complete. So that's an overview of both static and dynamic agents. Broadly, the static agents are broadly similar to traditional programming primitives, if then else and while loop and parallel, while the dynamic agents have unclear, they may allow all sorts of control flow at runtime. Control flow is not predetermined at the time of setting up these agents. Another good thing about this article is that it's really removed from the hype, and it advocates adding complexity only when needed. So I think that's the takeaway message from this article. You add complexity only when needed, and so these building blocks are not prescriptive. They are just common patterns that the authors have seen and the developers can shape, combine to fit different use cases. Of course, what matters is measuring performance and iterating on evaluating the current implementation and iterating based on the observations or feedback. The final, you should consider adding complexity only when it demonstrably improves the outcomes. Right, so the summary is nice to read. Try to follow 3 core principles: maintain simplicity, prioritize transparency, and craft your agent through thorough tool documentation and testing. Again, frameworks can help you get started quickly, but don't hesitate to reduce the abstraction layers and build with basic components as you move to production. So I found in practice often that it is useful to know what these key abstractions are, but often a very bare bone framework or even starting from scratch is useful in figuring out the task, how to implement them with agents. So thanks to Eric and Barry for writing this article. It's an amazing article very insightful, covers all the patterns, key patterns, and really removed from all the hype uh, which people uh, have around agents. There are two appendices with examples on customer support agents and coding agents, and how do you prompt engineer. Those are also very useful to read. Yeah, so that's a quick review of this article on building effective agents. I'll be talking more about agents and how to build with AI, and key programming patterns in following videos.